we will study how to determine transfer function from state space. That is, our main purpose is determination of transfer function model from state space model. So, first of all, in this case we will see introduction, conventional approach and some numerical examples. Till date we have seen that when transfer function is there or differential equation is there, we have converted into a state space model, and we have seen there are a lot of advantages of state space over transfer function. But today we are discussing the conversion of state space to transfer function. When the state space has so much advantage, why we are studying this conversion, that is from state space to transfer function? This is because in most of the industry, even nowadays, instead of advanced controller, a conventional controller has been used, just like a PID controller. And when we were designing a PID controller, that means we required a model, and if the model is in transfer function form, we have a lot of techniques so that we can easily design a PID controller. Therefore, sometimes we need a transfer function model. That is, when we have a state space model and we have to design a controller, PID controller, it is better first of all we convert the given state space model into transfer functions. That is first point. Suppose for a plant, if we have developed a model which is based on state space, but the main purpose is to design a controller, PID type of controller. That is, here main purpose is to design a classical PID type of controller. The most of the PID controllers design techniques are based on transfer function approach. The researchers have developed various tuning techniques, that is tuning of PID control parameters. They are based on transfer function approach. Therefore, in that case there is need to convert state space model into transfer function form. Now, next point, in control theory there is one area which is called model order reduction, and there also we are reducing higher order model to lower order. But if you suppose if the system is given in a state space form, then in that case to get the model is quite difficult, or the lot of technique which are available that is based on transfer function approach. Therefore, in that case what we will do, we have a state space model. State space model we have to convert into transfer function, then we reduce that model, and finally that reduced model we convert into a state space form. So, therefore, these are some advantages of having a transfer function even though we have a state space model. Now, how to get the transfer function model from when the model which is given to you is in state space form? So, let us see here we have model x dot equal to ax plus bu and y equal to cx plus du. So, consider the state space model like this. Now, what we want the model in transfer function form. Transfer function means that S domain. Therefore, what we are doing, we are applying Laplace transform to this equation 1. So, when we apply Laplace transform to this equation 1, we are neglecting initial conditions. So, here initial conditions are neglected. Therefore, we got model S x of s equal to a into x of s, and this is b into u of s. Similarly, y of s, c x of s plus d u of s, that is from 1 to 2 we have obtained a model, or model means we have obtained a transfer function form model, or transfer function equations we have obtained. So, now we have to solve this equation. How will you solve these equations? So, here what we do, we have taken si minus a one side and p into u of s. Then here what we have done, we have done x of s here, and si minus a we have moved on the right hand side. So, it becomes si minus a inverse into b into u of s. So, x of s equals to si minus a inverse b into u of s, and what is y? Y of s is c into x of s into d into u of s. just now here shown. So, what we do, we replace the value of x of s in this equation. So, when we replace x of s in this equation, what we will get? We will get y of s equal to c si inverse a b u of s plus d u of s. And now u of s and u of s we take in common, and then after solving, what we have got? We have got y of s divided by u of s equal to g s. Now, this is our transfer function model equal to c si a inverse b plus t. So, this is g s, that is the g s we have obtained for x dot equal to a x plus b u, y equal to c x plus d u. This is state space model, and this is equivalent transfer function, and you will find that in this particular transfer function we have a, b, c, d both are involved. Now, how to find out the transfer function? So, you will find that here we need to calculate the inverse, and when they need to calculate inverse, that means that we need to calculate its adjoining as well as determinant. Therefore, this equation si minus a inverse we have written in this form. What is the form? Adjoining of si minus a divided by determinant of si minus a, c, b and d. So, here the main purpose is to calculate the adjoint of si minus a as well as determinant of si minus a. Now, how to calculate? How to calculate adjoint of si minus a? So, first of all we define what is meant by adjoint of si minus a. So, adjoint of si minus a is defined as the transpose of cofactor of si minus a. That means, you have to calculate the cofactor of this si minus a, and then we have to make it transpose. Therefore, adjoint of si minus a equal to cofactor of si minus a transpose. Now, how to calculate the cofactors? The cofactors of si minus a is related to minors of a matrix. So, for every elements in the matrix there are some minors. So, that minors have to be calculated, and once we get the minors we will get cofactor, and once we get cofactors we will get adjoint. So, here steps have been written. A cofactor of si minus a is related to principal minors of a matrix. It is related to principal minors of a matrix. Suppose the minor of element aij is denoted by mij, I varying from 1 to n, j varying from 1 to n. So, the mij denote the ith and jth column of determinant A. The cofactor of the element aij is given as minor minus 1 raised to I plus j mij, and then we have to calculate the determinant of si minus a, and finally last step, replacing the values of si minus a inverse in equation 5. If you see we have shown equation 5, we get the transfer function model of the system. That is, the main purpose is to calculate the adjoint and also the determinant. Now, how to calculate the adjoint and determinant of a matrix? So, this is a matrix. For simplicity we have taken 3 cross 3 matrix. So, A11, A12, A13, A21, A22, A23, A31, A32, A33. So, let us say these are some elements, and this matrix A, and this matrix is a square matrix. Now, how to find out the minors of matrix A? So, in order to get the principal minors of matrix A, first of all I will take this A11, that is minor of A11 we have written as K11, that is equals to, just remove this row and these columns. So, what we will get? A22, A23, A32, A33. So, A22, A23, A32 and A33. This is this. Similarly, to calculate the principal minors of A12, remove this particular row and this particular column. So, what is remaining is A21, we have A21, A23, A31 and here A33. That is, this is basically your A21 and this is basically your A31, and here A23 and A33. Now, the principal minors of this A13. The principal minors of A13, remove this particular row, this column. So, we will get A21, A22, then this is A31 and here A32. Then about the principal minors of this particular element. The principal minors of this element, that is we have to remove that particular row and columns. So, here this row and this column has been removed. So, what we will get? We will get element of A12, A13, then we will get the element of A32 and this A33. Similarly, the principal minors of A22. So, A22 means particularly this row and this column. So, last element is you have A11, then A31, then we have A13 and then A33. Then the principal minors of this particular element A23. A23 means we have to remove this row and this column. What is? We have A11, A12, then A31, this one, and A32. Now, next we have to take the principal final of remaining element, that is particularly A31. So, A3 means we have to remove this row and this column. So, what element we will get? We will get the value element of A12, A13, then we will get the elements of A22 and here A23. Then the principal minor of A32. So, we remove this row and column. So, what we will get? A11, we will get A21, then A23. And lastly, the principal minors of A33, particularly this you remove this row and this column corresponding to A11, A12, then A21, then A22. Now, the cofactors of a matrix, cofactors of a matrix minus 1 raised to 1 plus j into Mij. So, whatever elements is get, you see the which rows and which columns, particularly when you see this particular element, this lies in your first row and first column. So, here I equals to 1, j equals to 1, so 1 plus 1 2, so minus 1 raised to 2 is 1. Therefore, its element corresponding to this is positive. Similarly, if you take this element or you can say this A12, so just see A12 where it lie, it lying in the first row, this is row 1, and what is the column? Column is 2, first column, sorry, first row, second column, first row, second column. So, 1 plus 2 plus 1 3, so minus of 3 equals to minus 1. So, you find that the element is negative. So, minus K12. So, if you check all the elements in this particular matrices, you will find that this and this, that is to say, you can say these particular elements, they have negative signs, all have positive signs, and therefore, what we want the adjoint of A, nothing but the transpose of cofactor of A. That means, once we get the cofactor of A by this arrangement, what you do? We have to make the transpose of the elements. To transpose means you have taken M11 here, M21, then here M31, see here M31, then here M12, then here M22, then here M32, and now here M13, M23 and M33. That is here M11, M12, M13, M21, M22, M23, M31, M32, M33, and now these elements you have to make transpose. That means M11, M21, M31, M12, M22, M32, and lastly M13, M23 and M33. So, in this way we have got the adjoint of A. Now, the calculation of the determinant. How to calculate determinant of a matrix? So, for determinant, what we do? Let us say A11, A12, A13, A21, A22, A23, A31, A32, A33. Now, how to calculate the determinant? So, to get the determinant, what I have taken? I have taken A11, then equals to this cross multiplication. That is similarly the adjoint. Here the procedure is somewhat same. That is, for this A11 we remove this row and columns. So, here A32 multiplied by A33 minus cross multiplication of A32 into A23, just here. Now, to get the A12, I have to use or negative sign I have used, because this lying in the first row, row is first row, and what is column? column is second. That is first row, this is first, and here is second. So 1 plus 2 3, so this is odd, that is minus 1 of I plus j, minus 1, that is we can say minus 1 of I plus j. So I is 1, j is 2, so minus 1 raised to 3 we will get minus 1, that is we get minus of a12, then a21 multiplied by a33 minus a31 into a23 this, and lastly a13 plus a13, that is equals to, remove this row and column, so we will get a21 multiplied by a32 minus 82 multiplied by a31. In this way we have to calculate the determinants of A. So here we have calculated the adjoint and determinant of A matrix. So this is particularly 3 cross 3 matrix. Similarly we can try for other order of matrix, and we will find that as the order increases the computation will increase, but nowadays because of software we are not facing such problems, but for theoretical point of view or from calculation point of view it is better to solve manually for lower order system. Higher order it is cumbersome. Now I am taking here one example. Example 1, determination of transfer function model from state space model using conventional approach. Now here I am saying a conventional because afterward I will go for some other approach which is somewhat better than this, but however the approach which now I am presenting is a conventional approach, that is whatever we have discussed, that is a conventional approach. Now x dot equals to 0 1 minus 1 minus 2 0 1 u y 1 0. So here we know A, this is B and this is C, A, B and C. So now we have to follow the steps. So we want a transfer function, that means what we want g of s for this plant. For g of s means C SI A inverse B plus D, this we required. As I discussed earlier, we want now SI A inverse first, because C is given, what is C? C10, and here B is also given, but we need SI A inverse. So how to get it? So first of all I have written SI minus A, that is nothing but SI means here S 0 0 S minus A. What is A? A is 0 1 minus 1 minus 2. So just you see it, S minus 0 S, then here 0 minus 1, then 0, this is minus 0 minus of minus 1, and here S minus of minus 2, that is plus 2, then S plus 2. So now we have got SI minus A. Now what we want its inverse. To get the inverse, first of all we determine the adjoint, and for getting adjoint we need cofactors. So cofactors of SI minus A. So to get the cofactors of SI minus A you will find, so here see a step. Yes, what is the cofactor of S? Cofactor of S is S plus 2. Cofactor of this element is 1, so you will find that here S plus 2, but now here it is written minus 1. It is minus 1 because here this is in the first row and second column. So whatever elements will get, that has to assign a negative sign. I mean, whatever elements will get here, we have to assign a negative sign. So here we are connected and attach a negative sign. Similarly, the cofactor of this one is 1, and here the cofactors of this is yes. Now what we do? We have to take the adjoint. Adjoint means what we do? We have taken S plus 2, 1 minus 1 into S, this we got adjoint, and then we require the determinant. So how to calculate the determinant? So determinant we calculate as here, this is right as this, yes, this S plus 2, then here we have plus 1, that is you will find here S square plus 2S plus 1, that means we will get, so we have got this S square plus 2S plus 1, that is the, we can say determinant. That is, again I will proceed this, how will we get this? That is we have S minus 1, here 1 s plus 2, and how will you get it? Here s square plus 2s plus 1. So, here basically it is minus 1. So, s minus 1, here 1 s plus 2, we get s square plus 2s plus 1. Okay. So, I think you have understood. See here the si minus a, we got s minus 1 s plus 2. So, we are s square plus 2s plus 1. Now, here we have got this adjoint of s1 minus a cofactor determined we have got. Now, we want gs. What is gs? gs equal to c si minus a inverse into b. What is c element? Which is c? C is our 1 0. So, we are at 1 0. Then si minus a inverse. Si minus a inverse we have already calculated it. So, we have s plus 2 1 minus 1 s, and what is the element of b? B is we have 0 1, b 0 1. Therefore, what we got? We got after solving this one, we got 1 upon s square plus 2s plus 1. So, this is one example we have solved. Now, we see we will solve some other example, and moreover what we will do, we will take two different state space model, and we will see that for two different state space model what type of results we will get. So, we start with an example. So, we will take example now here x dot equal to ax plus bu, this is, and y equal to cx, and here the model here I am taking as 0 1 0 0 0 1 minus 6 minus 11 minus 6. Here we write x1 x2 x3 plus 0 0 1 into u, and what is the output? Y 1 0 0 x. This is the example. This a b c has been shown, d is 0. Now, what we want? We want the state transfer function model. So, what is the first step? We have to determine si minus a. So, what is first step? Si minus a, this is si minus a. So, how will you get si minus a? The si minus a, that means how will you write? This is s minus 1 0, then here 0 0, and here this is 1, here minus a, it becomes minus 1, and here we will write 6 11 s plus 6, that is si minus a, we have got it. Now, next step we what we want? We want the cofactor of this si minus a. So, how you write cofactor? So, cofactor of si minus a. So, this is yes. Now, this is yes. S minus 1 0 0 s minus 1 6 11 s plus 6. Now, we call cofactor of si minus a. So, here particularly for this element we have to remove this row, this column. So, what we will get? So, we will get it as s square plus 6x, this one, and now here plus 11, s square plus 6x plus 11. Now, about this element you see minus 1. So, here you have to remove this row and this column. So, multiplication is s plus 6 into this, and here minus 6. So, and minus 6 and minus of minus 6 is plus 6. So, s square plus 6s plus 11, and here is 6, and particularly this one, this particular case. For this element we multiplied 11 and minus 6s. So, minus, that is minus 6s here, and then here for this row we can write the element like this, minus s minus 6, then s square plus 6s plus 11s plus 6, and lastly we write 1 minus s into s square. Now, afterward what we want, that this to get the adjoint, the we see that the elements, this signs of these elements to be changed, because all these 4 elements will lies in this minus 1 I plus j form. Therefore, the adjoint of elements is nothing but the cofactors transpose along with these particular elements. Therefore, we write this particular element s square plus 6s plus 11, then here this sign minus s minus 6 we write as s plus 6 plus 1, this one, then here 6, because of this minus 1 raised to 1 plus j, this element become minus 6 and here is minus 6, then this is s square plus 6s, then here we get minus 11s plus 6 minus 6 and here we write 1, this is s and this is square. So, we got cofactor of Si minus A. Now, we require adjoint. To get the adjoint, we have to make transpose of this. So, we write adjoint of Si minus A. So, adjoint of Si minus A. So, what we will take? We take transpose of this, that is equals to cofactor of Si minus A, this is transpose. So, we write down this as s square plus 6s plus 11, then here s plus 6, then is 1, then here minus 6, s square plus 6s, yes, then minus 6s minus 11s plus 6 minus 6 square. So, now we have got adjoint of Si minus A. Now, next step is we have to calculate the determinant of Si minus A. So, how to calculate determinant? So, we write determinant of Si minus A. So, determinant of Si minus means how to write? This is s, this one s square plus 6s plus 11, and now what this we have taken. Now, about this element, this 0, that means what we will get? We will get it as s square plus 6s plus 11s plus 1 and this 1 into, and about this is 0. So, all the element concerned with this will come 0. So, we will get it as s cube plus 6s square plus 11s plus 6. Now, we have got adjoint, we have got determinant, and now our next step is to calculate the model. So, your model is g of s equal to c Si minus A inverse B plus D, this is the model. Now, we replace the values. So, here we write our element C. What is the value of C is? C is your 1 0 0. Now, what is the value of B? B is your, check it, 0 0 1. You can check this here. So, here 0 0 1 is B and this is C. So, we have written here C and B. And what is Si minus A inverse? So, Si minus A inverse Si minus A inverse we have got as s square plus 6x plus 11 s plus 6 1 minus 6 s square plus 6s plus s minus 6s minus 11s minus 6 into s square, that is s square. Now, next step is we have to multiply this C Si A inverse B. So, here this C is 1 0 0 1 0 0, and here this 1 0 0 you have to multiply it with this Si inverse. So, if you multiply, let us say this is A, this part, this is A into B, A we can say AT, let us say AT, and now AT, and now here we have to multiply. So, what will get? If you multiply this 1 0 0 with this one, so what happens? All the elements concerning with this second row and third row will come 0. So, what we will get? We will get as s square plus 6s plus 11 s plus 6 to 1, that is C SI inverse. We have got this, and now it is to be multiplied by B. So, your B is 0 0 1. So, finally, after multiplications, what we will get? We will get as 1 up 1, and here SI minus is inverse is nothing but adjoint, but it will be multiplied by determinant. And what is the value of determinant? Is s cube 11s square 6s square plus 11s plus 6. So, here we got 1, and this is like this, s cube plus 6s square plus 11s plus 6, that is GS we have got like this. That means, you have a original model x dot equals to x plus bu. First of all, we have determined SI minus A, then we have determined cofactor of SI minus A, then we have adjoint. Now, adjoint how we have got? We are taking the transpose of cofactor of SI minus A, and while taking the cofactors, what we have taken, whatever the elements, in particular ith and jth row, if they are coming odd, we have assigned negative sign. Just see here minus 6 plus here minus 11s minus 6, and here minus s, which is, and then determinant we have calculated. After that, to this SI minus inverse we have multiplied by C and B. So, C is 1 0 0, B is like this, and after multiplications of all these C and B, we have got GS equals to 1 upon s cube plus 6x square plus 11s plus 6. So, this is the example which shows that we can convert the given state space model into transformation. Now, we will take another example. Now, another example, x dot equal to Ax plus Bu, y equal to Cx. Now, here model I am taking as A equal to minus 0 0 0 minus 2 0 0 0 minus 3, and B here we are taking as 1 1 1, and C we are taking as 1 by 2 minus 1 1 by 2. A, B, C we are taken. A is minus 1 0 0 0 minus 2 0 0 0 minus 3, B 1 1 1, and C we have taken as 1 by 2 minus 1 1 minus 2 1 by 2. And now we want the transformation model, that is we want G of S. So, now we will follow the steps which I have discussed earlier. The first step is we write SI minus A, SI minus A. So, what is SI minus A? SI minus A equal to S plus 1 0 0 0 S plus 2 0 0 0 S plus 3. We will find that the most of the elements in this case are 0, and this particular model which you have already seen last time, that is in diagonal form, and therefore it is simply SI minus A. So, we have taken S plus 1, S plus 2, S plus 3. Now, we have to determine the adjoint of SI minus A. So, for adjoining we required the cofactor of SI minus A. So, cofactor. So, let us say with respect to this element S plus 1, the minors are this S plus 2, S plus 3. So, we are multiplied this S plus 2 into S plus 3. Now, with respect to the 0 elements, the minors are 0 0 0 S plus 3, there is 0, and here 0. Then here with respect to S plus 2, with respect to 0 and with respect to another 0, the elements are this is 0, and with respect to S plus 2, here multiplication, this we have to remove this row and this column. So, there is a multiplication of S plus 1 and S plus 3. So, we write S plus 1, S plus 3, and here other element 0, and finally about third 0 0, here S plus 1 into S plus 2. That is with respect to this, the minors are this row and this column we have to remove, and here element like this. So, S plus 2 into S plus 1 into S plus 2. Now we have got cofactors, and after that we require the adjoint. For adjoining, what we do, we have to make the transpose of this one, and before transpose we have to assign negative sign. So here this negative, so all zeros, so there is no need to attach any or connect any negative sign. Therefore what we want, we have to take the transpose of this one. So but in transpose we will find that here, as this is a diagonal form, whatever be the cofactors of Si minus A, we are getting the same as adjoint of Si minus A. That means here your adjoint of Si minus A, here transpose of cofactor of Si minus A will get the same thing like this. Now the next step, we have to determine its, means we have to determine the GS. So how to determine GS? For getting the GS, we have to multiply C, then yes, then we have to determine, we have to say multiply by inverse. So here GS equals to C. C is your 1 by 2 minus 1, 1 by 2, and here we write this as S plus 2, S plus 3, 0, 0, 0, S plus 1, S plus 3, 0, then here 0, 0, S plus 1, S plus 2, and now we have to multiply, and this is the adjoint. What is the determinant? And determinant is nothing but S plus 1, S plus 2 and S plus 3, and C SI inverse, this is SI inverse, B is 1, 1, 1. Now first of all what we do, we multiply this with respect to this matrix. So you will get it as 1 by 2 S plus 2 S plus 3, then other element will get it as minus S plus 1 S plus 3, and here we will get it as 1 by 2 S plus 1 to S plus 2 divided by S plus 1 S plus 2 S plus 3. That means how we got it? Here we have multiplied this, so 1 by 2 multiplied by this, rest is 0, therefore we have got S plus 2 S plus 3. Then about this we have multiplied by this one, so regarding this first element, this one 0, 0, so remaining minus of S plus 1 S plus 3, so you see here minus of S plus 3, and here you will find that this 1 by 2, this all, sorry, 1 by 2 minus 1 by 2 is multiplied by these elements. So here 1 by 2 multiplied by 0, 0, minus 1 multiplied by 0, 0, and particularly but 1 by 2 when multiplied by S plus 1 S plus 2 we will get it like this, and this is S plus 1 S plus 2 S plus 3. Now this particular product, it is multiplied by B, so B is your 1, 1, 1. So now if you multiply actually, so what we will get? We will get 1 by 2 S plus 2 S plus 3 minus S plus 1 into S plus 3 plus 1 by 2, this is S plus 1 S plus 2 S square plus 3S plus 2, and divide by S plus 1 S plus 2 S plus 3. Now if you solve it, so what will you get? S plus 2 plus S plus 6, we will get S square plus 2 plus 3, 5S plus 6, so divide by 2, so what will you get? S square by 2 plus 5 by 2S plus 6 by 2 minus, here we will get it as S plus 1 S plus 3, that is S square, 3 plus 1 4, 4S plus 3 plus S square by 2, then 3 by 2S plus 1, and divide by S plus 1 S plus 2 S plus 3. Now you just see here this S square plus 2, this S square plus 2 by 2 become S square, and this cancel with minus S square. Then just see here, this is 3 by 2S, then here 5 by 2S, so 3 by 2S plus 5 by 2S equals to 4S, plus 4S is subtracted with minus 4S becomes 0, and lastly this is 3 6 by 2, but and is minus 3, 3 minus 3 will cancel, become 0, and finally we got it at 1 upon s plus 1, s plus 2, that is s plus 1, s plus 2, s plus 3, that is same thing, and we will write it down this as s cube plus s cube plus 6s square plus 11s plus 6. That means if you see it earlier, s cube plus 6s square plus 11s plus 6. So, we have got the same thing, s cube plus 6s square plus 11 plus s plus 6. Now, here we observe that we have taken two different state space model, but we have got the same transfer functions. It means that for a same, if you have one single transfer function, we have got different state space model, but when we have different state space model, we will get only single transfer function. That means the state space model are not uniques, but whereas the transfer function models are always unique. That means the state space models are not unique, whereas transfer function models are always unique. Now we have to see what are the drawbacks of this particular approach. So, we cannot say the drawback as because we are having a different state space model, we are getting the transfer function. So, that means the variety of information about the models we cannot get, because we are getting the same transfer function model. Now, the other thing is that here we will find that this need to calculate the inverse, but if you think say 25 years back, where there were no softwares, so that time the calculation of inverse is quite cumbersome. That means you have to call adjoining and determinant, all these things. So, as the order increases, it is quite difficult, and you know that if you take some example, power system models with a very high order model, so in that case it is difficult to apply this particular method. So, therefore, it is written here, as the order of the system increases, the mathematical computation burden will also increase. This is the one drawback. And second is that, let us say if you want to determine the transfer function from the given state space model by using the MATLAB software, maybe MATLAB software. So, in that case we have to take this s is a variable, so s is scalar. So, earlier time it was difficult to calculate the SI minus A inverse by means of a MATLAB. Nowadays it is possible. That is, second point is that earlier the digital computer fails to determine the SI minus A inverse because the Laplace operator S is a scalar. The Laplace operator S is scalar. However, nowadays due to advanced software, it is possible to find the inverse of SI minus A. Today there is no such problem to calculate the SI inverse, because of the MATLAB has been advanced, we can easily calculate, but if you see the earlier times, this procedure even it is quite difficult to calculate by means of any software. Now, next point is that sometimes we have to do some analysis of the system. So, in the analysis of the system, there is no need to use the actual values, there is need to use the variables. So, in that case, to calculate this SI minus inverse is also very cumbersome, even today also. So, that is why we want some method we can easily get the transfer functions. Therefore, in the next part we will going to study how to calculate the GS or transfer function model from the given state space model without computing the inverse. Now, these are some references. Thank you.